Hey guys, hope you guys are all doing okay. So this is part of the 433 megahertz you can't crack this project, and today we're going to be looking at the QiaChip Signal protocol. We're going to reverse engineer it. We're going to put it into a CC1101 and transmit it over to a QiaChip receiver and show that we can successfully do that. This is all part of my ongoing investigations into creating a rollJam. So I can understand how a rollJam attack would create a vulnerability for my project and how I can stop it. Okay, before we get into the detail of the protocol itself, let's have a look what we've got on the breadboard so you can see what's happening here. Here we've got a standard QiaChip transmitter with a standard QiaChip receiver. We've not got the microcontrollers connected, which is part of my project in this instance, because we're just going to simplify what we're doing here to make it more understandable. You can probably see that this pulse is flashing here once about every second, and that's because this transmitter over here, run by this ESP, is transmitting a signal. But all we've got is we've got the 4 buttons, and if I press in between a signal, I can press different ones. The only thing we've got here is this one's just simulating the button one press, and that's what we're going to talk through today. And just before we move on, one thing worth noting about this circuit is that we can jam the signal getting through from here to here by just pressing one of these buttons, and that's going to be really interesting when we come to do the rollJam effect. So if I just time that correctly, you'll see what happens is that my button press gets jammed by this signal, but also this signal gets jammed by the signal. In other words, it receives 2 signals and it can't make sense of it, so both turn off. And you can see it's still pulsing away. Try and give it a button 2 press. Button 2 comes on, and then in time with what this would be flashing, number 2 goes off. So basically, both signals are disrupting each other. Of course, we're going to need to control that when we come to rollJam, and of course we're getting we're transmitting on exactly the same frequency on a rollJam. The jamming signal to allow one to get through will be slightly shifted off. So let's crack on with the detail of the protocol itself. So the tool we're going to use to capture a signal is a program called Universal Radio Hacker. There'll be information in the description of some videos I've recorded that talks through installing all this software that I'm going to use here today. And I'm using an RTL-SDR.com software-defined radio, bought from Amazon, and it's a version 4 in this instance. So let's grab a signal. Now you can probably still see on my bench, should be able to still see on my bench that the LED is still flashing. So we're going to capture my CC1101 information coming across. First of all, I'm going to run through this as if I haven't done this before. So we'd go into the spectrum analyzer to see where our signal lies, so we can set our gains, etc., and our frequency. Let's have a look what we've got here. So that looks like our pulse. Okay, we're gonna just clear that. Sometimes when I'm doing this spectrum analyzer part, the radio hacker does actually lock up, but it comes back eventually. So let's just clear that and have a look what we can see. I'm going to turn the gain up just slightly because it's flashing around at the bottom a little bit for my liking. Let's try that. There you go. So that is definitely my pulse. So my pulse is definitely at, which is about right. I would have expected it to be more around about here, 3.8, but it's 4.4. That's good enough. 4.6 maybe. So I'm going to set my frequency just slightly off to the left there, and I'm going to do that by clicking on that, and notice how it's altered it here. And the reason why we do that is because it seems to struggle. If you get bang on the frequency, it doesn't always make a very clean recording. But I think that looks good. We can see the pulses coming up every second or so. Should be in time with this if my equipment's recording okay, with the LED flashing on the board. So that is exactly what we've got. We can see here these coming through. So that's all good. So I'm going to stop that now. I'm going to close that. and I'm going to use the signal recorder tool. This is now being copied across here. We can do this. The gain's been set, so we can do this, and that's a pulse, that's a pulse, that's a pulse, and we'll stop that there. We need to click save, and you can see how many of things I've been saving here and how much time this has taken. And if we close this, it'll be loaded into this window, and we can click this, but if it recognizes it straight away, it will have tried to decode it. And if I put this onto hex, then we see the signals. Now let's have a look what we've got. So we captured 3 signals, and what we can see here is we can see this is the start of the first pulse, and we can see that there's some sort of holding pulse going on here, and the same thing again, and the same thing again. So what I know from my research on this is that we need to receive this. I'm going to look into it a little bit more in depth in a minute, but the first part of this is going to be a unique code which identifies the transmitter being used and is paired to the QiaChip receiver normally, and the end bit is the actual button number that's been pressed, and we're going to show how I leverage that from 4 buttons into 15 codes to create a rolling code in my project. What I've also noticed is that you need at least one of these pulses, but only one if you've got a high level of interference. If you only transmit one, you're likely to miss, and then it will just ignore this line here. So I'm transmitting 4 for the best results in interference or high interference areas. I also note that this pulse here also changes depending on the unique code here, but it's always a combination of E's and 8's. And what I do see is if you line up like the B underneath is an E, again B underneath it an E, A underneath it an E, and a 2 underneath it an 8. And what I pick up from my tests at least, and I've only got 4 of these chips, is that if the unique code is a letter, then it's an E on this rolling part, and if it's a number, then it's an 8. So we should be able to manipulate that during the rollJam experience, and or it's worth noting for any sort of vulnerabilities in my project of how that might be computed, let's say, by a hacker. And we can see that here we've got a gap of 7,395 samples, and in a bit we will go through how to look at using how much each byte takes, or nibble actually in this case, takes to send the whole section in terms of time, so we can look at how we calculate the timing here to make sure that when I made this signal work, to make sure it was exactly 28.38 milliseconds, the same as the original device. So let's have a look at my analysis of the signal, and in the first part of this here we see that this is actually my project code, and these are the numbers that it's transmitting: a 2, an 8, a 10 and a 1, and you see each of these coloured lines here start off with the same numbers, if you like, codes, but then the last section change depending on what number's being transmitted. So this represents the 2, this represents an 8, this represents a 10, and this represents a 1. And you can see I was doing this on different signals, and then I was looking to see what changed, see where the errors lie or the changes lie, and then we get down to this level of analysis where we start to look at, so this is the unique code that the transmitter transmits initially, and the RX, the original QiaChip Rx, QiaChip Rx, will look at this code to validate it, to make sure it's definitely a bound transmitter before processing the last results. And these ones here in orange, these are the usual ones for button 1, button 2, button 3 and button 4. And these are the normal codes that it would normally send. And these white ones are where my project leverages using the buttons as a binary combination. So here I'm actually pressing button 1 and 2. So I'm getting a different combination code coming over, and 5, 6, 7. And we're using this to send a series of rolling codes over the air to the receiver, and using a microchip in the after the receiver to validate what those rolling codes are. Then we can detect whether it's actually the next rolling code in the loop. Also worth noting here is that if we take bit 0 here in this, so we've got a 1, a 0, 1, 0, 1, 0, and we look at bit 3 and 4 of this one, which is these two here, we can see we've got 1, 0, 1, 0, 1, 0. And then if we look at the bit 1 on this one, we've got a 0, 1, 1, 0, 0, 1, 1. And for those, we've got the combination of 7 and 8. So it's this 0, 1, 1, 0, 0, 1, 1, and so forth, using this table here. So we could, if we need to, we could use that information to break down the button presses or the codes in my case. And just to cover off, and I think we mentioned it already, so we said that the first part is the unique code of the transmitter, but just notice that these are different modules, TX module 1, 2, 3 and 4, all with button 1 being pressed. Notice that each one has a unique identifier, but also notice that the hold pattern also changes depending on the unique identifier. But I think, like I've already said, a 2 becomes an 8, or should I say a number becomes an 8 and a letter becomes an E, and it seems to follow that process all the way along. Just an extra nibble stuck on the end. If we're going to send these as bytes, you've got an uneven number of bytes going across. You've got an odd number. So if you were sending these as bytes, you'd have to send a nibble for the E and end in a byte, otherwise it doesn't work. So what I find quite interesting really about this point here is that all the rollJam programs that you find on GitHub and download off the internet just want to sort of receive a packet and send it again. And that's because most signals, if you look at doorbells, garages, etc, 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 they tend to just send this one packet probably 10 times in a row, and that's so they just grab one of them and send that back because it's all the same. But what's interesting about this one is that to actually make the receiver respond, it has to get at least the initial packet followed by at least one hold packet. And I say at least one hold packet because if you're in a high interference area, then one packet sometimes won't be enough and the receiver will not respond, which is why I would, on my project, I send 4. But it's just interesting to note that to create a correct roll jammer here, I'm going to have to code it a little bit like what we've got here with Universal Radio Hacker, where it actually records everything that's happening and plays back like a sample of the sound pattern in the air, if you like, to make it work correctly, rather than just record a packet into a buffer and try and play it back as it is as hexadecimal values. So I think that's an interesting note and makes it more complicated to reverse engineer and to create a rollJam hack. I would certainly put it out there now as either needing something technical in the sense of like this is working here to replay, and not just a packet grabber and a packet sender, if that makes sense. It's going to need to be something a little bit more technical, which means that somebody's going to have to put a bit more effort in, unless there is such a tool that will record this and send it back, which I suspect there might be. I suspect that there are options, maybe using the hack RF and things like that would just pick that up. But I don't know whether you can use a hack RF as a rollJam. I haven't got one, so I can't say. But if you could use a hack RF as a rollJam to record a signal and then send the previous signal like this back, then I would suggest that would work. So let's take a look at the program that I used to actually get this C1101 transceiver to send this correct signal over to this QiaChip receiver, and I have cannibalized the project that we was looking at the other day for the rollJam. So thanks to that guy, and a big shout out to him. Let me just get that on the screen so you can see it. So this is the original project that I have forked, and it forms the basis of my code I'm using here. Basically just cannibalized it. So big shout out again to that guy there. So all I've done here, if we scroll to the very top, is all this the same code as that project. All this just setting the where the registers are. I've commented out some of these, so the green lines aren't in play because I needed to change them. I used the Texas Instrument tool for the CC1101 to find some new settings here. And the key bits here is I've got a carrier frequency set like this. I've got a auto flush setup. I'm not quite sure about this because I'm not sending a CRC, so I don't know why it's put that in there. And the other bits is it's ASK based on what this found here, and I'm going to show you in a moment how I determine the data rate based on the speed to make sure we got the definite 28.38 here. What else is in there that we need? The preamble count. It's even said I'm having a preamble and I'm not having a preamble count. So this is all a bit weird, and it's come out the tool. That's what it says. I've got the settings for. So, but these clearly work for the QiaChip. This is all the same. I did alter some things so I could port it over. So it used to use this sort of code because it was bit bashing the registers in the Teensy, and I wanted to make it an ESP32 version. So I've just changed this here, and another version down below. So I've kind of commented this out instead, and instead I'm using actual numbers in that area instead, and just using digital writes instead of bit bashing the registers to see which pins are high and low. It's far better. I've just launched another video on that, actually looking at the difference between bit bashing registers and digital write, and we see that there's 0 speed difference. That's another video of mine you may want to watch. And essentially we get down here, and eventually we get here, and this is the bit that's important. So this is, I know it says jam data here, but I'm utilizing the code because again I'm probably going to keep cannibalizing this code. So the jam data is actually the initial line up there, and the hold data is the second pattern here. And as you see, again I'm transmitting 4 just because of the reliability. And I've just gone down here, if I can find where that's his is. So this is the pattern for the first line, and this is the holding packet for the 4 that follow. Let's look at the timing. So how did I work out my delay? We're using an ESP32 connected, so I've got 5,200 microseconds, which is obviously 5.2 milliseconds. So let's have a look how I work that out. So if we go here, and if we get a calculator, and we say, right, okay, so we've got the total length of the packet. It took 35.78 milliseconds. So let's go 35.78 milliseconds. And the packet itself took 28.38. So that should be 7.4 milliseconds. And then if we go back to our code, we see I used 5.2. Now don't forget that when it calls this to send this, then it spent some time sending it, so the delay wants to be less. And to be fair, I mean you could go into setting a stopwatch counter on here to see how long this bit takes. You could set your oscilloscope up, make a pin go high and then low when it's finished, and work out the exact timing. But what you find is on most of these things I've played about with is that you can just play about and see what works. And of course, if you're using Universal Radio Hacker, if you're looking for something like a pause of 7395, then you can go ahead and just keep testing it, altering the figure and making it right. So whichever works for you, really. Now the next bit we need to work out is, how did we work out the timing for this part, which is the most difficult part, really, I guess, and that is the data rate here. How did we work that out? So we jump back to the calculator. What we can do here is we can go, well, we know how long it took to send this here, 28.38 milliseconds. If we say there's 1,000 milliseconds in a second, and we divide that by 28.38, we know that we could repeat that sequence 35.23 times every second. So if we look at how many bits we've got there, well, we've got 12 bytes. 8 times 12 is 96. So if I times that by 96, that's how many bits we've sent. That means our baud rate is 3,382 bits per second. And we can enter that here. Now, you might say it's not precise. That is because the tool can do a little bit of rounding. Well, that turned out to be a much longer video than I anticipated, so I will put sections down below so you can just jump to the bits that you find most interesting. We're all pressed for time, I understand that. So I'll also put some links up here to the 433 megahertz You Can't Crack This project, and there'll be a GitHub link down the bottom if you want to get involved and have a go at building it yourself. And have a bit of a play. The initial equipment, the QiaChips, are a few dollars each. I mean, you know, it's not expensive at all, and it's a good learning curve. You can pick up the RTL-SDR.com software defined radio for 40 quid if you want the official version. There's like some for like, I don't know, a tenner, you know, $10, 10 quid, or whatever, for some clones. So it's really worth having a play about, guys. And I think with my videos about the installing and what you've seen here about how to read your doorbell signal, or you know, your temperature monitors, whatever you want to do, it's interesting stuff, and it might give you food for thought and a little bit of hobby time. Anyway, thanks for watching, guys. Please like, subscribe as always, hit that notification bell, and I'll see you on the next one.